So the kinetics topic is all about rates of reaction. And rates of reaction is something that you looked at GCSE, and it's something that will appear or does appear twice in the A-level course. And this obviously is the first time it appears in the A-level course. And really, this kinetics topic is really quite similar to what you did at GCSE, and it just builds on it slightly and introduces a particular graph. And really, that's how it extends the rates of reaction topic. But it still considers rates of reaction in a qualitative sense, in the sense that you can say that if you increase, and we'll go with concentration, then you increase the rate of reaction, and that's what you've been able to say. That's what you were able to say at GCSE. But you can only ever say it in a qualitative sense. You're never saying, oh, if I double this, I triple this, or I quadruple this, or whatever. You're never really making that sort of judgment, or you haven't done up to this point. When it comes to the post sort of AS content, when you do rate equations, which is the second sort of unit on rates of reaction in the A-level course, then you'll be talking about rates of reaction in a quantitative sense. So we actually start the kinetics topic with something that you've done before, you did at GCSE, which is collision theory. So what collision theory tells us is that if a reaction is to take place, then the particles involved must collide. When they do, bonds may be broken, new ones formed, but that collision isn't sufficient. It's necessary, but it isn't sufficient. So not only must the right particles collide, but they must also do so with enough energy to cause any relevant bonds to be broken. So the minimum energy for a reaction to occur between colliding particles, that's called the activation energy. And the activation energy is closely related to rates of reaction. So typically, the greater the activation energy, the slower the rate of reaction, and conversely, the lower the activation energy, the faster the rate of reaction. This is a useful rule of thumb anyway. Now at GCSE, you covered activation energy, and you would typically have labelled the reaction profiles that you did for exothermic and endothermic reactions. You typically would have labelled those showing the activation energy, and I think it's useful for us to just remind ourselves about those reaction profiles and how we labelled the activation energy with those. So let's look at exothermic first. So we briefly looked again at these reaction profiles when we did energetics topic. So really, these help illustrate the role of activation energy as a sort of energy barrier that must be overcome by reactants before they may form products. So here we can see the barrier illustrated in an exothermic reaction. And now we can see it illustrated in an endothermic reaction. So the fact that a certain minimum energy is needed to initiate most reactions is well illustrated by fuels and explosives, for example. So once these reactions have started, they supply the energy needed to keep them going. So it's really this area that is now a brand new sort of piece of knowledge as regards our understanding of rates of reaction. So using kinetic theory of gases and probability theory, the Scottish physicist James Clerk Maxwell and the Austrian Maxwell-Boltzmann, they derived equations for the distribution of kinetic energies amongst the molecules of a gas at a particular temperature. So our x-axis in this distribution curve is energy, and our y-axis is the number of particles or number of molecules that have that energy. And the distribution curve itself looks like this. So what can we tell from this distribution curve? Well, it tells us or shows us that only small numbers of molecules have either extremely high or extremely low energies. And we can also see that the curve is not symmetrical. So we can look at this a little bit more closely. Something to point out is that there are no particles with zero energy. Where the peak of the curve is, that represents the most probable energy, because that's where we have the greatest number of particles with that particular energy. The average energy of the system will lie slightly to the right of that most probable energy. The area under the curve will equal the total number of particles in that system, or the total number of molecules. And then what we could also include is we could label where, say, the activation energy might be, and then we can get a sense of the proportion of molecules or particles with energy greater than or equal to the activation energy, because it will be the area under that part of the curve. So what I'm shading now would represent the particles or molecules that had the activation energy or greater. So it gives us a sense, when we're thinking about collision theory, about the proportion of molecules or particles that will have the required energy for the reaction to take place. Now, when you did rates of reaction at GCSE, you looked at various factors that affected rate, and one of those was temperature. Now, one of the things that temperature does is that if you increase the temperature, you increase the kinetic energy of the particles. So you're increasing the proportion of particles with the activation energy or greater, and you're also, by increasing the velocity, which is what you're doing if you're increasing the kinetic energy, by increasing the velocity of the particles, you're also increasing the frequency of collisions. So we're going to look at that a little bit more closely now. So it turns out that if you do the maths regarding the frequency of collisions, if you raise the temperature of a reaction by, say, 10 Kelvin, the maths tells us that we would increase the rate of collisions by approximately 6%. So there would definitely be an increase in the rate of reaction, but not a sizable one. However, when actual experiments have been performed where the temperature has been increased by 10 Kelvin, then we're seeing roughly a double the rate of reaction. So, roughly 100%. So the maths tells us the collisions increase by 6%, but the experimentation tells us that the rate doubles so it's a 100% increase. So what this is telling us is that raising the temperature has a much greater effect on the proportion of particles that have the activation energy or greater than it does really on the frequency of collisions. And the Maxwell-Boltzmann distribution can help us understand or appreciate that a little bit better. So here's our original Maxwell-Boltzmann distribution at a particular temperature. And what I'm going to say is that's the intermediate temperature. Okay. So we're going to look at what the curve looks like at a lower temperature and what it looks like at a higher temperature. So we'll consider first how the distribution curve looks at a lower temperature. So what we can see is that the peak of the lower temperature distribution curve lies to the left of the original, and which makes sense because that means the most probable energy of the lower temperature curve is less than it would be of the intermediate temperature. We can see that the peak of the lower temperature is higher also. And we can see that it only crosses the original or our intermediate temperature line once. So sometimes in exam questions, they can give you a curve and then ask you to sketch a second curve, either at a lower temperature or a higher temperature. If they ask you to sketch it at a lower temperature, then what you've got to make sure that your curve shows is that the peak is to the left of the original, that it is higher than the original, and that it only crosses the original once. And what you should never have is your line to the right ever touching the x-axis. It gets closer and closer, but you shouldn't have it touching. What about if it was at a higher temperature than our intermediate temperature? So we can see that the curve at the higher temperature, the peak lies to the right of the original, it's lower, and it only crosses the original once. So these are the sort of sketches you would have to do. Obviously, you'd probably do a slightly better job than I've managed to draw here, but you get the basic principle. If we now add the activation energy onto a graph, we can now see a little bit more clearly how changing the temperature has such a dramatic effect on the rate of reaction, because if we look at now at the proportions under each of those curves, we can see that they are changing by a significant amount each time. So I know these are sketches and I know it's the way I've drawn them, but they're getting across the idea that raising that temperature by 10 Kelvin actually has a significant impact on the proportion of particles that has the activation energy or higher, and therefore has a significant effect on the rate of reaction. So this is one of the absolutely one of the brand new things that is part of the A-level chemistry course as opposed to the GCSE. So we're getting a greater sense of the effect of changing the temperature. The effect of concentration and pressure on the rate of reaction, our explanation as far as this kinetics topic is concerned, is essentially identical to what we did at GCSE. So increasing the concentration of the reactants typically increases the rate of reaction. I've used that word typically. At GCSE, we would have said definitely. And really, as far as this kinetics topic is concerned, we will still say definitely. But when we come to do the quantitative part of rates of reaction, so when you do rate equations, you'll discover that changing the concentration doesn't always increase the rate of reaction. In fact, it doesn't always affect the rate of reaction at all. So that's something for the future. But for the moment, yes, we'll assume it does increase the rate of reaction if we increase the concentration. And essentially, when we're saying a greater concentration, and we're looking at something like the box on the right, we're saying there are more particles in a given volume. Now, this has the effect it does because now we have shorter distances between the molecules, and so we are increasing the frequency of collisions. And please, please, please use the word frequency or chance, because I've often found students say something like the number of collisions increases. Now, the thing is, if you have a reaction happening, the same reaction happening, and we have the same proportions of reactants, eventually, when the reaction is complete, it doesn't matter whether it was fast or slow, the number of collisions will have been the same. So you're not actually affecting the number of collisions. What you're affecting is the frequency of those collisions. So please be very careful with your language. Pressure is essentially a way of affecting concentration when we're talking about gases. So for reactions involving gases, increasing the pressure increases the concentration. And so again, there's an increase in the frequency of collisions. And again, typically an increase in the rate of reaction. So nothing radically new from what you did at GCSE there. Similarly, the catalyst, which is the final part of the kinetics topic, so it is quite a short topic. It does involve doing practicals, but in terms of content or knowledge, there's not a great deal to it. And the idea of catalysts fundamentally, again, is exactly the same at GCSE. We're just going to reintroduce the Maxwell distribution curve in a second. But essentially, a catalyst is anything that increases the rate of a chemical reaction without actually being changed in chemical composition or amount. So sometimes it is involved in the reaction and so gets regenerated. And sometimes it is just really a surface on which the reaction takes place. But overall, and this is the important thing, overall there is no change in the chemical composition or amount of that catalyst. So what you'll never see is a catalyst appearing in an overall reaction equation, because it would be the same at the end as it was at the beginning, and then therefore in effect cancels out when you're doing a reaction equation. So it'll never appear in an overall reaction equation. And how do they work? Well, they work by providing an alternative reaction route at a lower activation energy, and that is this final bullet point here on the screen here. This is a fundamental point. And so sometimes there can be an exam question that asks you how catalysts work. And if they're not talking about a specific one, if they're talking about catalysts in general, then this is your 2-mark answer. So lowering the activation energy, most students don't have any problems recalling that, writing that. But where they often fail to get the 2nd mark is because they haven't mentioned that that catalysts achieve this they result in a lower activation energy for that reaction. They do it by providing an alternative reaction route. And so you've got to have that as part of your answer also. So we'll just finish by illustrating the effect of a catalyst by considering our Maxwell distribution curve. So if we just put the activation energy for a particular reaction, we just place that. And we know that using a catalyst lowers the activation energy, so we will put that activation energy using a catalyst there as well. And now when we consider the proportion of molecules that have the activation energy or higher or greater, then when we compare the original, which is now shaded in grey, with the one with the catalyst, which is the grey and the purple, we can see there is a much greater proportion of particles with the activation energy or higher. So that concludes the kinetics topic. There isn't really very much to it that extends from the GCSE, only really the Maxwell-Boltzmann distribution. It has got a required practical, which really just considers how rates of reaction are affected by some of these different factors. But I hope that all made sense, and if you have any queries, just let me know.